Assalamualaikum and a good day. My name is Shakirah binti Mat Saleh. On behalf of the other authors, I would like to present our short paper entitled Long Short-Term Memory on Electricity Load Forecasting, Comparison of Feature Scaling Techniques. Here is the outline of our presentation. We will start with the introduction, review of related works, methodology, results, analysis and discussion, and conclusion and future works. In certain countries such as United States, electricity generation contributes 25% of the primary sources of greenhouse gas emission. The greenhouse gas emission impact climate change by trapping heat that leads to global warming. The United Nations has introduced 17 Sustainable Development Goals (SDG) that emphasize a holistic approach to achieve sustainable development for all. The 7th SDG goal is affordable and clean energy. Renewable energy is currently being used in several countries such as Denmark, which generates 45% of its electricity from wind. However, not all countries can afford renewable energy yet. Electricity load forecasting is important for electricity supplier because it can assist them to generate electricity sufficiently as for heat. Overgeneration of electricity incurs additional costs to the electricity suppliers in generating more than the demand, and additional carbon emission will be produced during electricity generation. The machine learning algorithms that support time series and regression include current neural network and long short-term memory (LSTM). The electricity load range has a major difference between peak and non-peak hours. The feature scaling techniques help to minimize the impact of one significant number on the model by bringing various features in the same standing. The studies did not always sufficiently justify the effectiveness of the selected feature scaling techniques by comparing it with other feature scaling techniques that may influence the model efficiency. The major objectives of this article are to identify the range of the scaled dataset using the MinMax Scaler, Robust Scaler, and Power Transformer Scaler, to compare the evolution metrics of the model generated by the training dataset scale using the MinMax Scaler, Robust Scaler, and Power Transformer Scaler, and to compare the electricity load between the actual and prediction values generated by the model. In this study, we applied the supervised learning. The output of electricity load forecasting is a numerical value that represents the prediction results. The most suitable method to predict the continuous value of electricity load forecasting is regression. RNN is employed in time series prediction because it can save the output of a layer and feed it back to the input. Throughout the learning cycle, the gradient values that carry information become too small and insignificant. LSTM can overcome this vanishing gradients issue in RNN by remembering information for extended period. LSTM works in form of chain of repeating modules of a neural network with 4 interacting layers that communicate with each other. By using RNN and LSTM, the data input transform from a 2-dimensional array into 3-dimensional array. Feature scaling techniques, also known as scaler, shift and rescale values into a certain range without altering the distribution values. Feature scaler helps to minimize the gap in dataset value. A series of article reviews were made to identify the common feature scaling techniques by other researchers. 10 out of 17 review articles applied MinMax Scaler in their studies. It is challenging to find related works that use Robust Scaler and Power Transformer Scaler in electricity load forecasting. The model generates from the training phase requires evaluation process to determine its quality. The common evaluation metrics used for regression problems are mean square error, root mean square error, mean absolute percentage error, and R-squared. Based on the review made earlier, 2 rarely used feature scaling techniques were considered in this study, which differ from the commonly used scalars in the similar case study, and their impact on the output of the selected algorithm, LSTM. The predictions obtained from such process input lead to increased accuracy, as demonstrated by the result obtained. The hourly electricity load prediction was forecast using historical data from the previous hour with 7 days of memory use. The dataset used in this study was a residential areas in Denmark between 2015 and 2018. The dataset consisted only one feature, the previous hour electricity load that was represented hourly. This figure shows the navigation diagram of the implementation of LSTM in this study. The highlighted processes are critical in achieving the objective of this article. The dataset consists of the date, time, electricity load data of the specific date and time, and the electricity load data of the previous hour. The data selection process selected the feature to be used in this training and testing phase. Since the machine learning algorithm used was LSTM, the dataset needed conversion from 2D into 3D array. The components of the 3D dataset were sample, time steps, and features. The time steps used in this experiment were 24 and 168 to compare the effectiveness of LSTM in memorizing the electricity load pattern every 24 hours and 7 days. These are the list of hyperparameters used in this study. The experiment used the epoch value of 100. However, the early stop mechanism was applied in this study to control the training session so as not to overfit the model. The results compare based on the time steps, the 4-month samples, and the models generated from the experiment. For the scaled dataset, the minimum value produced in robust scaler is negative 1.898697. The maximum value is 4.122344. For the power transformer scaler, the minimum value produced is negative 7.349004, and the maximum value is 3.518321, and the maximum value generated in MinMax Scaler is 0 for minimum and maximum is 1. The first experiment started with the LSTM model generation using 24 hours of memory that was presented by time steps. The second experiment commenced with the LSTM model generation using 168 hours of memory information represented by time steps. And as you can see over here, the result that we get for R squared is the highest for model R168 compared to the other model generated in this experiment. This figure represents the prediction by the model generated using 168 steps. The actual value represented in red. The value predicted by robust scaler is represented in blue. The green line represents the prediction by power transformer, and the purple line represented the value predicted by MinMax Scaler. The MinMax Scaler only limited the data range to be scaled between 0 and 1. This results in the scaled value becoming too small. The robust scaler scaled the dataset between negative 1 and 5, while the power transformer scaled the dataset between negative 7 and 3. This range was double as compared to the robust scaler. The result of the model evaluation metric focused on R squared since it compared the actual and predicted value. The MinMax Scaler performed the lowest R squared value as compared to the other scalars for the 24 time steps and 168 time steps. The R squared value between the robust scaler and power transformer scaler was very competitive for each sample month for both time steps. However, the highest R squared value was scored by the robust scaler when the time steps were set to 168, which represented 1 week of memory information. The impact of climate change has become obvious from day to day. This research indirectly supported the 7th SDG goal of affordable and clean energy by comparing the mechanism that could better predict electricity load since electricity generation contributes to the primary source of greenhouse gas emission. This study intended to compare the various feature scaling techniques as they are toward the prediction values. The common feature scaling techniques used in the reviewed studies was MinMax Scaler. The other feature scaling techniques used for comparison were robust and power transformer scaler. The robust scaler could minimize the outliers, while the power transformer scaler could transform the dataset into more Gaussian-like distribution. The machine learning algorithm used in this study was LSTM because of its ability in memorizing information to solve regression problem. This study also proved that the ability of LSTM in memorizing information for a certain period could improve the model quality. In total, there were 6 models generated in this study, and the best model generated was model R168 with an R squared value between 0.90 and 0.95. This model was generated by training session of 168 times with the robust scaler dataset. For the future works, The current study used the SYNC activation function due to the nature of the dataset that had rise and falls in 24 hours of electricity load consumption, which look similar like sine wave. Future studies should compare the effectiveness of using the other activation functions such as rectified linear activation function ReLU and TAN hidden layer activation function. This is another opportunity to explore since this article has proven that the commonly used feature scaling techniques MinMax Scaler is not always the best scaler to be used. That's all from us. Thank you.